Having considered benzene and its molecular orbital diagram in some detail, we now turn our attention to the question, are there any aromatic compounds besides benzene? So benzene can be thought of as 1,3,5-cyclohexatriene, so the next molecule to think about might be 1,3,5,7-cyclooctatetraene. This would have the molecular formula C8H8. Well, this compound exists, but it is actually not especially stable. So when it has been investigated structurally, instead of having 8 equal bonds, which would be analogous to benzene, it has 4 longer bonds and 4 shorter bonds. And so our interpretation is it actually has 4 single bonds and 4 double bonds. So there's a difference. And reactivity-wise, it behaves like a normal alkene, undergoes the reactions characteristic of alkenes, and not like benzene. Furthermore, more detailed structural investigation has revealed that the molecule is not planar. In fact, it is a tub-shaped boat. So it is clearly not aromatic. And in fact, the lack of planarity precludes this molecule's ability to have the delocalized overlap of p orbitals that are necessary to give the pi molecular orbitals characteristic of aromaticity. The next molecule we can consider would be cyclobutadiene, C4H4. Well, this molecule has never been isolated in macroscopic quantities. It has been isolated in cages, single molecules at a time, at very, very low temperatures near absolute zero, frozen in argon. Now, you may say that this molecule would be too strained to exist based on angle strain. But these observations are consistent with something that is even more unstable than you would expect based on angle strain alone. So far, it seems like benzene is unique in its aromaticity. But there are more aromatic molecules that are known. So this led a chemist named Erich Huckel in 1931 to postulate what is now known as Huckel's rule, which says that a molecule will be aromatic if the following 3 conditions are met. First of all, it would have to be a cyclic conjugated system. That's chemistry speak for there's a ring with alternating single and double bonds. And now the important part, that is planar. Secondly, there needs to be a p orbital on every atom in the ring. So the hybridization can only be a maximum of sp2 at any carbon atom. And then third of all, there needs to be a total of 4n plus 2 pi electrons where n is an integer. So what that means is that if you had n equals 0, 1, 2, 3, and 4 respectively, 4n plus 2 would be 2, 6, 10, 14, and 18. Now, you can't have a ring with only 2 pi electrons, assuming you're going to have alternating single and double bonds. So the smallest possible ring would be n equals 1, having a total of 6 pi electrons, and that is benzene. So based on Huckel's rule, benzene is aromatic, and that is, of course, what we observe. We would then also expect, based on Huckel's rule, aromatic compounds with 10, 14, and 18 pi electrons. Cyclobutadiene has 4 pi electrons. Cyclooctatetraene has 8 pi electrons. Based on Huckel's rule, neither compound is aromatic, which is what is consistent with what we observe experimentally. Okay, so 14-annuline and 18-annuline, those are the names of these, are both aromatic compounds. There is a 16-annuline, and as expected, it is not aromatic. Now, you may wonder why I skipped over 10. There is actually no aromatic compound with 10 carbons, because if all the double bonds are cis, you're going to have too much angle strain. The interior angles would have to be 144 degrees. There are, however, polycyclic aromatic hydrocarbons. So you may have heard of a compound known as naphthalene. It's the active ingredient in mothballs, has a very distinct aroma to it. And naphthalene looks like it's two benzene rings that are stuck together. In fact, we call this a fused bicyclic system. And if you look at the structure, there are 5 double bonds, at least drawn in the Kekulé structure, and therefore there are 10 pi electrons. And this compound is in fact aromatic, just it uses 2 rings instead of 1 ring. Moving larger to 3-ring systems, you have 2 arrangements, or 2 common arrangements. You have anthracene, where the 3 aromatic rings are fused next to each other in a row, and then you have phenanthrene, where the 3rd ring is fused above the 2nd ring. Both of these have 14 carbons, 10 hydrogens. There are 14 pi electrons, and since 14 is also a Huckel number, they are also both aromatic compounds. And then just to look at what the orbitals will look like for naphthalene, you can see that every carbon is going to be an sp2 hybridized, and therefore there is a p orbital on each carbon that can overlap with the other p orbitals to form the pi molecular orbitals, the bonding ones and the anti-bonding ones, just like we saw in the last video for benzene. Okay, so we've established Huckel's rule as an empirical rule. But what we need to do is understand at a slightly deeper level why it is true. What is special about 4n plus 2 pi electrons to make these compounds aromatic, whereas the compounds with 4n pi electrons are not aromatic? In order to do so, we have to look a little more into molecular orbital theory, and that's what we will do in the next video.